Alright guys, welcome back. So before the break, we're trying to show more and more problems to be NP-complete. And using 3SAT, we're able to show that independent set was NP-complete, meaning vertex cover and click are also NP-complete. I introduced this subset sum problem to you guys, and I didn't prove to you that was NP-complete. You can check the textbook for the proof, but it is in fact NP-complete. And we're trying to show that this partition problem is NP complete. How are we going to show that? Well, to show that partition is NP complete, we have to take another NP complete problem and reduce that NP complete problem to partition. Well, we know subset sum is NP complete. I'm going to try to show how we'd reduce subset sum to partition, but that's like we talked about this last time before the break, that's going to be a little tricky. Because over here, I'm given a set of integers and a target t. I wonder, is there something that sums up to t? Is there a subset of that set of integers s that sums to t? Well, is it going to help me to know if I can split a set up into two equal parts, like partition? I mean, t can be anything. This is just going to tell me if I can split it in two. T could be, far from half the sum value. So how am I going to do that? Well, here's the idea. I'm going to give you the reduction first, and I'm going to prove to you that the reduction works. So here's the first step. Well, first step will come after I'm given this. Given, I've been doing a lot of graphing problems. I should be saying given S and T. So this is an instance of the subset problem. I'm given a set S, and I want to know, is there a subset of S that sums exactly to T? And you should be able to write that down in language form as well. Okay, so given an instance of the subset sum, first, create a new set of integers. And I'll call that set S prime. What's S prime going to be? Well, it's going to be equal to S union something else. And essentially it's going to be S plus one more number. So it's the set of all the numbers in S unioned with one more number. What's that number going to be? Well, it's going to be lowercase s minus 2 times t. What's lowercase s, you might ask? Well, again, if you remember from the last part, lowercase s is just going to be the sum of all the numbers in that set of integers s. Okay, so this new set of integers is my original set of integers with one more number. Remember, t is a number, s is a number, s minus 2t, it's just a number. Okay, how does that help me? Well, ask my partition black box is there a partition of S prime? If yes, then we return yes to this original question of, does there exist a subset of S that sums exactly to T? And if no, we return no. Now, some of you, your first instinct to this is, okay, even if this reduction does end up working out, Vince, like how in the world are we supposed to come up with something like that? How do we know, like, oh, what if we add this specific s minus 2t to that? It seems like it's so, arbitrary, so random. It actually isn't, and we can talk a little bit about that, after we've seen the proof. But, deciding to do this is basically just working backwards just a little bit, and it's kind of like, once you understand the problem, it's a pretty intuitive thing to try out. Okay, so what has to be true for this reduction to work? Well, if this reduction works, for this reduction to work, I need partition of S prime if and only if there's a subset sum of S and T. So this reduction works if there's a partition, or there is a partition of S prime, if and only if there's a subset sum of ST. Well, in order to prove this, I need to show two things. First, I need to show, okay, a partition of S prime implies there's a subset sum ST, and I need to show if there's a subset sum ST, that implies there's a partition in S prime. So it's going to be two steps. Let's see if we can tackle it, one step at a time. First, I'm going to try to show that if there's a subset sum of S and T, then there is a partition of S prime. Okay, so subset sum implies partition. And when I say subset sum, I mean subset sum of ST and partition of S prime. Okay, let's consider the set S. I don't know if you can hear that, but it's my dryer telling me my laundry's done. Okay, so I have this set S, and I'm trying to show that subset sum implies partition. So I'm just going to assume that there is a subset sum in here that sums exactly to T. So I can think of, in S, I can split this up into S1 and S2. And I'm going to say, again, use some you could say bad notation, but I'm going to let S1 at the same time equal the set, the subset of values, and be overloaded to also equal the sum. So I'd say things like this. S1 equals T, meaning the set of all the numbers in S1 equals T. And I can do this because I'm assuming there is a subset in S that sums exactly to T. So I know I can make some subset S1 that sums to T. Well, what does that mean for S2? What's the sum of all the numbers in S2? Well, do we even know? Yeah, we know, because I know S sums to lowercase s, so this has to sum to lowercase s minus t. Okay, so that's the set of numbers s. What if we consider then s prime? Okay, well, I know that s prime is really just s plus one more number. So I know that s1 is still in here. And I know s2 is still in here. What remains? Well, it's some set s3. But remember, s prime is just, s1 and s2 is just s plus what? Plus one more thing. Plus this number. So you can think S3 is really a singleton set, and it sums up, because it's a singleton set, there's one number in it, that one number in it is S minus 2t. So I can also say S3 equals S minus 2t. Okay, well, these are my, so what? Those are some building blocks to the proof, but what I'm really trying to show is there's a partition in this set. Well, I need to find a P1 and a P2 that sum up to equal values. And they, the union of them equals S prime, and the intersection is the empty set. What might I try? Well, I have three subsets here. Let's just say, well, let's see what happens when I let this equal S1 union S3. And let's let P2 equal S2. That's what remains. So first of all, we have to make sure, is this a valid potential partition at the very least? Well, all the numbers are accounted for. The union of these two things equals S prime, and the intersection is the empty set because these sets don't overlap. So I have S1 and S3 here and S2. That's what I'm going to let equal my partition. In some ways, it's like I'm removing that little barrier there and making my partition just this and this down here. But let's look at what these partitions actually are, or these sets P1 and P2 actually are. So far we haven't violated anything from the definition of a partition. But what's the sum of all the numbers in P2? Let's look at P2 first of all. Well, P2 is just S2, so we can just say the sum of everything there is S minus T. And again, I'm overloading my notation to have P2 be the set of all the numbers P2 as well as the sum of all the numbers in P2. But P2 just equals S2, therefore the sum is just S minus T. Okay. Well, what about P1? Well, okay, do some quick math. Well, it's S1 and S3. So it's going to be T plus S minus 2T. Okay, so what? Well, we're third year, fourth year computer science students. This is what all our mathematical foundations have been leading up to. Because check this out, right? Addition commutes. I can rewrite this like so. Oh, hold on. What's going on here? Can factor a t out of that. Whoa. 1 minus 2. Get out the calculator. I get t times negative 1. Hold on, I can bring that out in front. I have to have a little bit of. Oh, so I can simplify this to s minus t. Whoa. That's pretty cool. Why is that cool? Well, I mean, it's cool in the context of 363. Why? Check it out. P1 and P2 sum to the same values. Well, hold on. If that's true, that means P1 and P2 are a partition of S prime. So, if there's a subset that sums up to T in S, then there is a partition of S prime. Sweet. Okay. So that's the first step. What's the second step? Well, remember, first step is proving subset sum implies partition. Second step, we have to show that partition implies subset sum. Okay, so step 2. Partition implies subset sum. Okay, so I look at S prime, and remember, I'm trying to show partition implies subset sum, so I'm going to assume there's a partition of S prime. So I'm going to have a P1, and I'm going to have a P2. Well, what do P1 and P2 sum up to? Well, think about it. What's the total value of this set of S prime? So if I were to sum up all the numbers in S prime, what does that equal? Well, remember, it's the sum of all numbers in S plus that number we added. What was the number that we added? Well, that was S minus 2t. So that equals, I'll do the algebra a little quicker this time. So that equals 2 times S minus t, which means each partition has to sum up to S minus t. And that shouldn't be any surprise, especially if you follow along from over there. Okay, so assuming I have a partition, I know P1 and P2 both sum up to S minus t. Now let's think, what numbers do those partitions include? Do those sets P1 and P2 include? Well, it could be an arbitrary number of numbers in there. Depends on the cardinality of S, how large or how small S was to begin with. Uppercase S, the original subset sum set. But what number do I know for sure exists in there somewhere? Well, remember, we added that number S minus 2t, and that was just a number. That's a single number. I know that number exists in one of these two partitions. It has to exist somewhere. Remember, the union of the two partitions has to equal S prime, so that number is indefinitely one of them. And without loss of generality, let's assume it's in P1, okay? So I know, okay, well, within P1 here, I know there's an S minus 2t. Because I know that single number exists. So let's say it's in P1, and P1 is this entire thing, okay. Well, if P1 is everything over here, plus this number S minus 2t, what's, the remainder of this over here? What if I call just this part over here X, and then like P1 is this part and this part, if you can understand what I'm saying here. X is essentially P1 with S minus 2t removed. Well, the one thing I know for sure is X is a subset of S. Why do I know that? Well, remember, S prime is S just plus one number. The only way a subset of S prime wouldn't be a subset of S would be if that subset of S prime happened to include that number S minus 2t. However, that's not the case because we've explicitly removed that number from P1 to create X. Okay, so we know for sure X is a subset of S. Well, what's the next step? What does X sum up to? Well, think about it. The sum of all the numbers in X. What is it? Well, it's the sum of all the numbers in P1 minus this number, minus S minus 2t. Well, what does P1 sum up to? S minus t. So this equals P1 minus S minus 2t, which equals S minus t minus S minus 2t. So this is where things get a little bit tricky. We have a negative sign outside the brackets. So pause the video, see if you can figure this one out. 5, 10, maybe 15 minutes, come back, and I think we can solve this together. Okay, 1, 2, 3, we're back. Well, you just have to be a little bit careful here. This becomes a plus. Well, hold on. S minus S, 2t minus t, we know that from our previous derivation of the first part, that works out to just t. Whoa. What did we just show? Well, we assumed there's a partition in S prime. And we said, well, given a partition in S prime, we can come up with a set of numbers X that's a subset of S, and the sum of those numbers in X sum up to T. Therefore what? Therefore, in S, there's a subset that sums to T, which means the subset sum should return a yes answer there. So yes, there is a subset sum in S that sums to T, given there's a partition in S prime. That means we've shown there's a partition in S prime if and only if there's a subset sum of ST, meaning that reduction we wrote initially, showing that subset sum reduces to partition, holds. What does that mean? That means partition is NP complete. Okay, so it's not that hard of a proof actually. It's just, for me, very counterintuitive, because you look at partition, it just seems so much easier than subset sum. It seems like a tier of generality below it. But what do we find out here? They're on the same tier of difficulty. They're both NP complete problems. So back to the original question, well, how would we know to add this s minus 2t in there? Well, like I said before, it's just a little bit of working backwards. Essentially, you know, in the first part of this, when this was a 1, and we're showing that given the subset sum implied there's a partition, well, you look at that, you look at, okay, I have t, I have s minus t, what number would I have to add to this set to create a partition? You just do the algebra, it turns out it's s minus 2t. So for me, it's one of those like kind of cool reductions, and again, 363 levels of cool, but this is kind of a fun problem. Okay, so moving forward next week, and maybe I'll get the lectures out, you know, relatively quickly, so sooner than that. But we're gonna look at least one more class of complexity, and just a little bit of a teaser here. This lecture we looked at NP complete. Next lecture we're gonna look at NP hard problems, and that's where this course really comes full circle. And not to give it away too much, some of you are going to be like, oh, geez, when you hear this, but you know, things like the halting problem and the membership problem are going to come back when we're dealing with this class of complexity. But that's for next lecture. Thank you very much for your attention. I'll see you then.